like, share, subscribe.
Hey y'all, welcome back. Today we're trying to practice solving rational inequalities. So the first thing we want to do is find the x values that make both the numerator 0 and the denominator 0. And these x values will be these potential x values that tell us when the value of the rational inequality changes from positive to negative or vice versa. So the values that we get by setting the numerator equal to 0 and then solving that, like here we get -6, that's going to represent an x-intercept of that rational function. So as I find these x values, I want to place them on a number line. I'm going to wait until I get all of the x values so I know like where they need to go in relation to each other. But once I get them, I'm going to place little tick marks on here and use that to help me identify what intervals are going to solve this rational inequality. So as I was saying before, the x values that make the numerator 0 are going to correspond to the x-intercepts of the function, and the values that make the denominator 0 are going to correspond to places on the graph of that rational function where it's undefined. Okay, so the value of this rational function can change from positive to negative or vice versa at these x values, either the x-intercepts or where it's undefined, and those are actually the only places where it can happen. So here I'm trying to factor this. Two numbers that multiply to give me 8 and add up to 6 are going to be 4 and 2, so I can rewrite this as x plus 4 times x plus 2. And so the two x values that make the rational expression undefined are going to be -4 and -2. So I've got three values that I'm going to mark over here on my number line: -6, -4, and -2. And I'm going to also make a little note on whether these are going to be places where the function is 0 versus being undefined. So like the x-intercept at -6, the value of the function is 0. At -4 and -2, the function is undefined. So I'm just going to make a little mark here, like a 0 or a U for undefined. And the reason why I'm doing that is because the solution set of this inequality is going to include values where this is 0, because notice this is greater than or equal to 0. So what we're looking for are intervals where the value of this rational expression is either positive, greater than 0, or actually equal to 0. And since it could be equal to 0, we're going to include this -6 in our solution set. So not -4, not -2, but I'm just making a little mark here as a reminder for when I actually do go through and write my answer that I do want to include -6, and I'll show that with a little bracket. Okay, so at this point, I need to choose representatives for each interval. So I'm going to pick one number between -∞ and -6, one number between -6 and -4, and then one number between -4 and -2, and finally one number between -2 and infinity. So the representatives I think I'm going to pick are going to be -10. Okay, so I'm going to pick -10. Let's see, maybe I'll, there we go. So I'm going to pick -10 for that interval. I'm going to pick -5 for this interval. I'm going to pick -3. And finally, I'll pick, I guess I'll just pick 0. And I'm going to go through, I'm going to plug this in and decide, hey, is this thing positive or negative? And make a little note on my little number line chart here. So if I plug in -10, I'm going to get a negative divided by, and then in factored form, this denominator is x plus 4 times x plus 2. So that would be a negative times a negative, right? So this negative times a negative is positive, and a negative divided by a positive is negative. So this one should be negative. If I plug in -5, I'm going to get a positive on top, And then on the bottom, I'm going to get a negative times a negative. So negative times a negative is positive, so a positive divided by a positive is positive. Between -4 and -2, I picked -3, and that's going to give me a positive divided by a, let's see here, a positive times a negative. So positive times a negative is going to be negative, and then positive divided by a negative is going to be negative. I'm going to get real sick and tired of saying positive and negative by the end of this, aren't I? So I'm going to plug in 0, and I get a positive divided by, let's see here, a positive times a positive. Everything's positive here. So the overall value of the function is positive. All right, so going back to what my answer is going to look like, I'm trying to find the values where this rational expression is greater than or equal to 0. So either positive or 0. So I'm going to choose this interval here between -6 and -4 because it's positive. I'm also going to include -6 because that endpoint is 0. I'm not going to include the endpoint of -4 because it's undefined there, so there's no value there anyway. So it's not 0 and it's not greater than 0. And then the last interval I'm going to pick is going to be from -2 to infinity. So the way I write that is I'm going to write x, and instead of writing equals to, when you're saying x is just like a specific number, you typically write x equals. But when you're trying to say that it is like when x could be any number in a set, then you're going to use it's kind of a stylized lowercase epsilon symbol, epsilon being a Greek letter. Let's see, and let me pull that up real quick. Cami does not have an epsilon symbol natively, so I have to copy it over from somewhere else online. All right, so it's this little symbol right here. It kind of looks like a C with a little E going through, and really, like I said, it's just a stylized epsilon. So x, and then what it means is an element of the set. So it's saying that x could be basically any number in between -6 and -4. And I'm putting a bracket around -6 because it could be -6. I want to include that value in the solution set. I do not want to include 4 because it's a -4 there because it's undefined at -4. So I want to put a parenthesis, not a bracket. So that, in case you were wondering the difference between the brackets and the parentheses, it's really just like whether or not you want to include that endpoint or not. Now I do have two sets here. The next set would go from -2 to infinity. And then the symbol you'll use to sort of join these two sets together is called a union symbol. And it's basically just looks like a U in between the two sets. So what you're saying here is that x can be any number between -6 and -4 and between -2 and infinity. So that's our solution set, and that's how you're going to write your answers, okay? So instead of writing, if you're just solving an equation with a finite number of solutions, you'll write like x equals and then just write the 1 or just like list them out. But if x can be infinitely many solutions in between values, then this notation is preferred. I think what I'll do here is make a little note that these are the x-intercepts. I think I did this on the notes as well, and these are where the function is undefined. And the only reason I'm doing this right now is because I think I just want to copy and paste this all the problems are going to be worked out kind of the same way. So what I'll do is just like copy and paste this format of like how I'm showing my work. So you can see that the strategy here is basically going to be the same for all these. And so just to kind of get something set up here for the next couple problems. Okay, so here we go. So I'm going to go through and erase, everything that I don't actually know yet. In fact, let me pause the video so you don't have to watch me do that. Ta-da! All right, just like magic, I've got a nice little template here to help me solve this out without having to spend too much time drawing up everything. So with number 2, we're going to solve it pretty much exactly how we did number 1. The only thing is we're looking for where this rational expression is negative rather than positive. So to find the x-intercepts, we are going to set x plus 3 equal to 0. So we get x equals negative 3. And to find where it's undefined, we're going to set the denominator equal to 0. And so that's x squared minus 5x plus 6. That is factorable, and we can factor it as x minus 2 times x minus 3. So the two x values that we get where the function is undefined are going to be at x equals 2 and x equals 3. So these are going to be all the values that we place on our number line here. So we've got one at negative 3. We've got one at, 2 and 3. So I'm going to need 4 representatives because I've got 4 intervals here. I'm going to pick negative 10, 0, 2.5, and I guess we'll go with 10. So I'm going to plug these in and figure out whether or not I'm positive or negative. Now, on the first problem, I really kind of broke it down and showed like, okay, well, it showed the sign of every little factor. But as we go forward, I'm just going to kind of do that mentally. I'm going to sort of explain, talk through it, but it just kind of takes too long to draw all these out. So, let me know if you have any questions, if something doesn't really make sense, or if you notice I make an error or something. But I'm just going to jump straight to calling the sign of the interval. So if I plug in negative 10, for instance, the numerator will be negative, and the denominator would be a negative times a negative, which would be positive. So a negative divided by a positive is going to be negative. Between negative 3 and 2, I can plug in 0, and so I'll get a positive divided by a positive, so that would be positive. Plugging in 2.5 will give me a positive divided by a, positive times negative would be negative, so a positive divided by negative would be negative. And I encourage you to check this, make sure that you're getting positive and negatives as you plug these numbers in. I know I'm going to run through this pretty quickly, but I'll let you do the arithmetic on your own. So if I plug in 10, I'm going to get a positive divided by, a positive, everything's positive here, so this is going to be positive. So I'm looking for values that are either negative or equal to 0. So I need to make sure I make a note that the x-intercept of negative 3, that is where the function equals 0, and these values of 2 and 3 are making the function undefined. Okay? So my solution set here is going to be all the values where the rational expression is negative or equal to 0. So that's going to be between negative infinity and negative 3. And I am going to include negative 3 here, so I'm going to put a bracket. Union, and then, what's the next one? 2 to 3. And since both of those endpoints are undefined, I'm not going to include either, which is why I'm using the parentheses on those. All right, so there's number 2. Let's look at number 3. So for the x-intercepts, x squared minus 9, that's a difference of 2 squares. I might use this as an opportunity to just remind you that if you have a squared minus b squared, that's going to equal a plus b times a minus b. Okay, so this is just a quick little factoring trick. It's called the difference of 2 squares. And the reason why it's called that is because, quite literally, it is a difference of 2 squares, right? You've got 2 squares, and you have a subtraction symbol in the middle, so that's a difference. And so it's the difference of 2 squares, yeah. So that's why it's called difference of 2 squares. So the reason I bring that up is because here we have x squared minus 9, so that can be factored as x plus 3 times x minus 3. I guess I'll start with the original one here. So, let's go back to the equation here. So we got x plus 3 times x minus 3. So the x-intercepts are going to be at positive 3 and negative 3. The denominator is just a linear expression here, so this one will be pretty easy to solve. All we have to do is just add 5 to both sides, and so I'll get just x equals 5. So once again, I get 3 values to place on my number line. Negative 3. Oh gosh, it's really, I need to work on my mouse drawing skills here. This is kind of tough. Okay, there we go. And then, so we got negative 3, 3, and 5. So yeah, I apologize for these being kind of sloppy, but I'm using a mouse over here. So if you ever try to write with a mouse, you know it doesn't go very well. So my representatives are going to be negative 10, 0, 4, and then I guess I'll go with 10. And so let's go ahead and start plugging these numbers in to get a feel for the sign of this. Let's see, so negative 10, if I plug that in, I'm going to get a negative times a negative, so that's going to be positive divided by a negative, so we're negative right here. Okay, between negative 3 and 3, if I plug in 0, I get a negative divided by a negative, so that's positive. Plugging in 4 will give me a positive divided by a negative. And if I plug in 10, I get a positive divided by a positive. It's going to be positive. Now, this problem is the first one where we have a strictly less than symbol. So there's no equal to underneath here. So in that case, it doesn't really matter which one's 0, which one's undefined. But it is good to just like get in the habit of always marking it. So like, you know, I've got a 0 here, I've got a 0 here. And then over here at 5, we're undefined. So I'm just going to put a little u here. Okay, so let's go ahead and write our solution set here. Okay, so we're looking for the intervals where it's negative. So it's going to be negative infinity to negative 3. And in this case, we are not going to include 3. And then I'll have this little union symbol. And then from 3 to 5. All right, and that's the solution to number 3. And number 4, we see the first problem that doesn't already have a 0 on the right-hand side. So for problems like this, we do need to do a little bit of algebraic manipulation using the properties of equality to get this number to go over to the left-hand side and force the right-hand side to be 0. So the first step in doing so would be to add 1 to both sides. So we'll have something like this. And then the next thing is, in order to kind of really start going with the rest of our strategy here for solving these, is we want the left-hand side to just be a single fraction. So a rational expression, one being where we have a polynomial in the numerator and the polynomial in the denominator. So we do need to combine these, and to do that, what we need is a common denominator. And so in order to get an x minus 4 on the denominator here, we need to multiply 1 by x minus 4 over x minus 4, okay? So something like this. Oops. All right, when we do that, 1 times anything is just going to be that anything, so we just get this. And now we can combine these two fractions, okay? So to combine them, we'll have 3 plus x minus 4. So we can combine the 3 plus the negative 4 will be negative 1. So our numerator is going to end up being x minus 1 over x minus 4. And now we can go through the same steps that we did previously to find our solution set. All right, so to get the x-intercepts, looks like there's just going to be one of them. I'm going to set x minus 1 equals 0, so x is going to equal positive 1. And the values where the rational expression is undefined are going to be when x minus 4 is 0, when the denominator is 0, and so that's going to be at 4. So for this one, we're only going to end up with 3 different intervals because we have 2 different numbers to mark on our number line, 1 and 4. So the representatives I'm going to use here are going to be 0, I'm going to use, I'm going to go with 2, and I'm going to go with 10. So if I plug in 0, I'm going to get a negative divided by a negative, so we're going to be negative there. And between 1 and 4, I picked 2, so that would give me a, I'm sorry, a negative divided by a negative would be positive, my bad. If I plug in 2, I'm going to get a positive divided by a negative, so that should be negative. And if I plug in 10, I'm going to get a positive divided by a positive, so that would be positive. Now the inequality symbol here is less than or equal to, so it is important that I distinguish the x-intercepts, where the function is equal to 0, from the places that the function will be undefined. So I want to make sure I include this endpoint of -1 when I'm listing all the solution, all the sets in my solution set. So the first one, the first set where the rational expression is negative is going to be, actually there's only one, okay? There's just going to be in between 1 and 4. And so we'll include 1 but not include 4. All right, so yeah, that's it for number 4. Let's take a look at number 5. All right, now number 5, we got a 0 on the right-hand side, so we don't need to worry about rearranging anything. Now what we do have is, yeah, and this is already factored, so that's kind of nice. So the numerator here is x squared plus 1 times 2x minus 5. All right, and so now with that first factor, that x squared minus 1, if I subtract 1 and then take the square root, what I'm going to get is...
Good morning, everyone. Just a reminder.
Like I was saying, when we subtract 1 and then take the square, we're going to get plus or minus the square root of -1, which is our imaginary I. So we really get like I and negative I here. These are not real numbers, so they don't exist on our real number line. So they're not really going to have any impact on anything past just finding that they're there. So we do get I and negative I, but we don't actually need to include those on our number line. And then the other one would be 5 halves. So yeah, so let me just, so that we don't need to include these. There we go. All right, so for the x values that make the denominator 0, our denominator here is x plus 1 cubed. So we are going to have some multiplicity on that root. And then times x minus 1 squared. So we do get a triple multiplicity on this one and a double multiplicity on this one. Now, really, there's not going to be, until we start graphing these rational functions, you're not going to really have to worry about the multiplicities too much here. This -1 would have a multiplicity of 3. Now, what I will point out, though, is that when you have an even multiplicity like 1, quite often what happens, I almost want to say it always happens, but I'm gonna hedge a little bit here, is that when you have an even multiplicity, the sign won't change there, versus when you have an odd multiplicity, the sign will change. So we'll check and see if that's what happens here. I don't want to assume that quite yet, without knowing that 100%, but I have noticed that's happened every single time. So let's place really we just are going to have three numbers on our number line, 1, -1, and 2.5. So let's go ahead and put those on there. So we have -1, 1, and 2.5. That's the 5 halves here. And it's going to be 0 only at 5 halves. Not that it matters for this problem because we have just a strictly less than situation here, but I'm just going to mark it anyway just to stay in the habit and make sure I don't forget on the ones that where it does matter. So representatives here, I'm going to pick -10, 0, I guess I'll go with 2, and 10. So if I plug in -10, so this right here, this one's always going to be positive because I'm squaring the number. So I'm just not going to consider this one because if I multiply by a positive, it's just not going to change the sign. The only thing that'll change the sign is if I multiply or divide by a negative. So since this will always be positive, I'm not going to even consider it. So for same thing over here, since I've got x minus 1 squared, that's always going to be positive. So really the only two factors that I'm going to be substituting in here mentally are going to be the 2x minus 5 and the x plus 1. So if I plug in -10, I'm going to get a negative divided by a negative, which will be positive. If I plug in 0, I'm going to get a negative divided by a positive. So it's going to be negative. I've got that multiplicity of 2 here. My theory is that we are not going to change signs at this even multiplicity. So let's see if that happens. If I plug in a 2, I do get a negative over a positive, so it does remain negative. So my theory still stands here. This might be something I might go look back into and see if I can prove this is true for all cases. I haven't done that, so that's why I'm hesitating to say that it always works. But it's always worked so far. Yeah, just finding examples where it happens is not proof. So that's why I'm hedging a little bit to say I'm just not totally sure if that happens every time, but so far it has. If I plug in a 10, I do get a positive divided by positive, so that's going to be positive. So the solution set is going to include all the values where this is negative, and that's going to be in between -1 and 1. And 1 and 2.5. And so here is the solution set for number 5. On number 6, looks like we got to do a little factoring to the numerator here. No big deal. We need to find two numbers that multiply to give me -40, but add up to positive 3. So one's got to be positive, one's got to be negative, and they've got to be pretty close to each other because the difference here has got to be 3. So let's see, factors of 40. We got 10 and 4. That's too far apart. 15. No, 15's not 1. What am I talking about? 20 and 2. I'm getting too far apart here. Let's see. 4 and 10. Is there anything? Is this even factorable? Or am I missing one? 4 and 10. 8 and 5. Yeah, there we go. So we got positive 8 and negative 5. So with my numerator being x squared, x squared plus 3x minus 40. We can factor that, and our two factors are going to be x plus 8 and x minus 5. So the two x-intercepts that I'll end up with here are -8 and +5. Now, one thing you might start to notice here, you might have already seen it, I haven't mentioned it yet, but let's just see what happens. For my x values that make the function undefined, I just have x minus 5 equals 0, so I get x equals 5. Now, right away, I'm seeing a little red flag here because I'm getting the same value. It's supposed to be an x-intercept, but it's also supposed to be undefined. So Whenever this happens and you have like the same factor in the numerator and the denominator, in this case we've got x minus 5 in both the numerator and the denominator, there is something consequential about that, and in the next unit when we look at rational functions a little bit more closely, we'll go over exactly what that means. But for now, all you need to know is that when you have a value kind of in both of these lists, the one that is going to override the other is that it's going to be undefined, okay? So if you get a factor in both the numerator and the denominator that are the same, that x value is actually going to make it undefined, and you will not have an x-intercept there. It's almost like an extraneous solution here. So I'm going to cross that out of my x-intercept lists. It is going to be undefined there. And that's actually going to be relevant when we write our solution set, because look, it's greater than or equal to, Oh, wait a minute. Okay, we got to back this up. All right, so for number 6, this one we don't have a 0 isolated on the right-hand side, so we're going to have to take care of that. Similar to how we did number 4. Okay, so just to kind of go back to number 4 real quick, we had to add 1 on both sides and find a common denominator, and we're going to have to do that here as well. So I'm going to start by subtracting 10 from both sides here. I can use the right tool. Here we go. So minus 10 is greater than or equal to 0. And then I do need a common denominator. So I'm just going to kind of do this in one step here because I don't have a ton of room. All right, yeah. Well, here's what I'll do. I'm going to move this down a little bit so that maybe I don't have to do it all in one step. Okay, so I do want to find a common denominator, which is going to be x minus 5. So I'm going to multiply that negative 10 by x minus 5 over x minus 5. All right, so now I've got a common denominator, so I can combine these. Before I do that, I want to distribute this 10 and make this 10x minus 50. And so now I can just combine my like terms and figure out what my numerator and denominator are going to be here. So the x squared has no like terms to combine with, so that's just going to stay the way it is. Here I've got 3x minus 10x, so it's going to be minus, 3 minus 10 is going to be negative 7x. And then I've got negative 40 minus negative 50, so minus the negative is going to be positive, so it's going to be plus 10. All right, so there we go. Now we can find the x-intercepts, the places where the function's undefined, and so forth. So to find the x-intercepts, I need to set the numerator equal to 0. So this x squared minus 7x plus 10, that is going to be factorable. And what we get here is going to be x minus 5 and x minus 2. Now, this will be the first problem where what we're about to talk about has occurred, and you may already kind of see what's going to happen if you're paying attention. If not, we'll talk about this momentarily. But we get x equals 5 and we get x equals 2 here. Now, as for the places where the function becomes undefined, that's going to be wherever the denominator is 0. This is just a linear equation, so all we have to do is add 5 to both sides and get x equals 5. Now, take a look at this. We've got an x value that is supposed to make the function equal 0 and simultaneously make it undefined. So, well, what sort of wins out here? It can't be both. You can't have the function have a defined value and simultaneously be undefined. So what ends up happening here is this x value that makes the function undefined will sort of override the x-intercept, okay? Now there is a little bit more significance to this x value that we'll talk about in more detail in the next unit when we look at rational functions a little bit more closely. But for right now, all you need to know is that as you're solving this, if you end up with the same value in both of these columns here, and both the x-intercepts and the undefined, then it'll be undefined only, okay? So if you're going to write your number line and you don't even catch it and you're like, wait a minute, I've already put 5 on there, do I need to put it again, or what's going on there? It's gonna be undefined. Now in this problem, it actually makes a difference because we're looking for values where this rational expression is positive or equal to 0. So you want to make sure that we do not include 5 as one of our zeros. So that can kind of throw off your solution set if you put a bracket on there when it really should be a parenthesis. So the representatives I'm going to pick for this one, I'll go with, I like to go with the easy numbers here. We'll go with 0, I guess 3, and then I'll go with 10. So if I plug in 0, then I'm going to get a positive over a negative, which is going to be negative. If I plug in 3, I'm going to get a negative divided by a negative, which is positive. And if I plug in 10, I'm going to get a positive divided by a positive, which is, oh, wait a minute. Hold up here. Did I mess something up here? Why am I getting positive here? Oh yeah, okay. So, before, this is okay. This actually checks out because, and now I'm just starting to think about, what the graph of this looks like. And this is something that we'll get into, like I said, more in detail in the next unit. But just like when you have these even multiplicities, this is going to be another case where, now this one, I won't say will always stay the same sign. If you've got like this, this number on both these lists, it is possible it changes. So I'm not going to place a rule on this. This one happens to not alternate, but if the whole happens on the x-axis, it could alternate. So you're going to have to test this no matter what. So no trick here. The trick, my theory is only holding for this even multiplicity business. So let's go ahead and write our solution set here. We're trying to find where it's greater than or equal to 0. Now it is going to be equal to 0 when x equals 2, but not when x equals 5. So at 2 we do have a 0. At 5 it's undefined. Okay. So my solution set is going to be from 2. I'm sorry. From 2 to 5. And from 5, we don't actually want to include 5 because it's undefined there, to infinity. All right, so there is number 6. Number 7, this one's kind of nice. Not only do we have 0 on one side, but it's already totally factored out. So this one shouldn't be too bad. No x-intercepts here. We can't set 1 equal to 0, so we're just going to say there are no x-intercepts, which means this function will never equal 0. Okay, and there are, looks like 2 locations where it's going to be undefined. We have x plus 3 and x minus 5 as our factors. So we're going to get 2 x values that make the function undefined, and that's going to be at -3 and 5. The -3, oh, we switched over to black all of a sudden, okay. Let's try to fix that. There we go. Oh, nope. Here we go. X equals -3 and x equals 5. Now, this -3 does, I want to point out, have an even multiplicity, specifically of 2. And so we are, if my theory that I've been holding holds up here, then we should not see a sign change at that x value. So this will be another good test to see if that is actually true or not. So I'm going to mark -3 and I'm going to mark 5 on this number line here. And the representatives I'm going to pick are going to be negative 10, 0, and 10. Now the numerator is always positive here because it's just 1, so I don't have to worry too much about that. Both of these are going to be locations, both of these x values are locations where it's undefined, and not that it really matters because we don't have less than or equal to, just strictly less than. But yeah, so I'm expecting no sign change at negative 3, so let's see what happens. If I plug in negative 10, or actually take a look at this. So this factor is squared, so this is always going to be positive. So this one is really the only one we need to check. So negative 10 minus 5 is going to be negative. If I plug in 0, I get a negative. So yeah, so my theory still stands here, where we don't have a sign change when we have an even multiplicity. And then if I plug in 10, I'm going to get a positive value. So if the inequality is saying we want to know where the rational expression is less than 0, it's going to be in between negative infinity and all the way to 5, although we're going to leave negative 3 out of it because it's undefined there. So the way we're going to state that is negative infinity to negative 3, and then the other set will be negative 3 to 5. So that'll be your solution set. So there's number 7. Let's take a look at number 8. So up here, this is not going to be factorable. In fact, if we try to solve it, we get x squared plus 1 equals 0, and so we're going to get x squared equals negative 1. So x is going to be the square root of negative 1, or rather plus or minus the square root of negative 1. Oh, didn't put that in there. Let's try again. Why is it? There we go. Now, this is not going to be a real number here, and we saw this once before where this is, potentially happens. We do get plus or minus I here. So we get I and we get negative I. But neither one of these are real, so they're not going to be values that we can place on the number line, and so we end up with really no x-intercepts. Okay. There is going to be one value that will make the function undefined, though, and that's going to be 5, because if we set x minus 5 equal to 0 and add 5 to both sides, we're going to get x equals 5. That's going to be the only number that we have on our number line here. And this is going to be a place where it's undefined, so I'm just going to put a little u here. And then so my representatives, I guess I'll pick 0 and 10. Seem to be, I think that'll probably work. Now that numerator will always be positive because we got x squared. So we're really just checking the denominator here. And if I plug in 0, I get a negative number. And if I plug in 10, I get a positive number. So negative on this side, positive on this side. And so if we're looking for where the expression is greater than 0, we're going to report back this interval right here. So from 5 to infinity. And so there we only get one interval. And so that's it. That's our answer for number 8. Okay, now number 9. Ooh, we can really jack up the difficulty level here a little bit. So what we've got to do is we've got to, first we've got to find a common denominator. We also need to bring the 4 over to the left. And then once we've got a common denominator on all 3 of those, we can combine them and write it as a proper rational function here. So let's see here. First thing we want to do is subtract the 4. So we're going to have 3 over 2 minus x plus 3 over 2 plus x minus 4 is less than or equal to 0. And so to find my what do I want to say? My common denominator here, I need to multiply this fraction by 2 plus x over 2 plus x, multiply this fraction by 2 minus x over 2 minus x, and then multiply this one by both. Okay, and then I'll have my common denominator across the board. So this one I'm going to multiply by 2 plus x, And this one I'm going to multiply by 2 minus x. And I'm going to have to clean up, I'm going to have to put these in parentheses to make sure my order of operations doesn't get messed up. And then I'm going to need to do the same thing with the 4, but I'm going to have to multiply both of these. So we're going to have really minus 4 times 2 plus x times 2 minus x, like this. Okay. So wow, that got this did get a little out of hand here. No big deal though. Okay, so the next thing I'm going to do is I'm going to try to simplify this a little bit. I'm going to do the distributive property here and multiply. Basically, I'm going to rewrite all of these numerators so that they are polynomials and they're not factored out. So I'll write them all in standard form. Here I'll have to FOIL out these two binomials and then multiply by 4. So I'm going to try to do all that, and then I'll start combining my like terms. So this will be like 6 plus 6x. I'm sorry, 6 plus 3x. This one will be 6 minus 3x. So actually, it looks like this is going to simplify pretty nicely here. I'm going to multiply these first. So that'll give me 4. Let's see, what would that be? Minus 2x plus 2x. And then minus x squared. And just to kind of save a little bit of room here, you know what I'm going to do? I'm going to make these a little small. I'm going to shrink the font size on these just a tad, because this is getting kind of out of hand, I think. I think you would agree. There we go. Okay, so I do want to distribute this forward here. I'm going to go ahead and do that right now. So this would be 16. 4 times 4 is 16. 4 times negative 2 would be negative 8, and positive 8, and then minus 4. Okay. So that way I don't need these parentheses. So now I can go through and just start combining all my like terms and write this just as one big old fraction, as opposed to 3 of them. So I'm going to just end up with a single fraction here. So let's see, I've got 6 plus 6, so it takes me up to 12, minus 16, that's going to be negative 4. And then we've got 3x plus negative 3x, those cancel out. Minus 8x plus 8x, so those are gone. And then the only squared term is going to be this positive 4x squared. So just kind of rearranging this a little bit, I'm going to put 4x squared minus 4, just to kind of clean that up a little bit, write it in standard form. And then I think what I want to do here is factor this out as much as I can. But I guess I could do that down here when I start solving for all the x-intercepts and where it's undefined. All right, so now that I got all that settled, I've kind of cleaned up my expression. Now I can go ahead and just start solving. So to find the x-intercepts, I'm going to set 4x squared minus 4 equal to 0. So if I divide both sides by 4, this will be just x squared minus 1 equals 0. And this is another one of those difference of two squares, or you can just solve it using square roots. And what you're going to get is x equals plus or minus 1. For the denominator, the values that will make the rational expression undefined, we've got 2 minus x is one of the factors, and then the other factor is 2 plus x. So the two values that we'll get would be 2 and negative 2. So we're going to have a total of 5 intervals here because we've got 4 values to place on the number line. We've got negative 2, negative 1, 1, and 2. And this is less than or equal to, so it is important that we make a note of where the function 0 and where the function is undefined. Okay. All right, so the representatives I want to pick here are going to be, let's do negative 10, negative 1.5, I'll go with 0, 1.5, and 10. So if I plug in negative 10 here, let's see what I got. So negative 10, this will be 100, 400, so that's going to be a positive divide. Now this one's getting a little complex, so this is going to be the first time where I go back and actually do write what it is that I have here. So yeah, if I plug in negative 10, I'm going to get a positive as far as the numerator goes, and then for the denominator, I'm going to get a positive times a negative. So this whole thing should be negative. Okay, if I plug in negative 1.5, 1.5 squared would be like 2 point something, so that would be, it's definitely going to be more than 1, so the numerator is going to be positive. And then the denominator is going to be, if I plug in negative 1.5, it's going to be a positive, positive, so this will just be positive here. If I plug in 0, I'm going to get just negative 4 over 2 times 2 is just positive, so it's a negative over a positive over a negative. Wait, am I saying that right? Hold on, let's back it up here. If I plug in 0, I'm going to get 0 minus 4. Okay, so that's going to be a negative over, if I plug in 0 here, that's positive, 0 here, that's positive, positive times a positive. All right, so this whole thing is going to be negative. If I plug in 1.5, I'm going to get a positive divided by a positive times a positive. So once again, we got a positive interval. And then finally, if I plug in 10, I'm going to get a positive over a negative times a positive. So that's going to be negative. And since I'm looking for where the function is less than or equal to 0, we've got these intervals, negative infinity, negative infinity to negative 2, and that's going to be an open interval because we are not going to include negative 2 in our solution set. And then the next interval would be from negative 1 to 1, and both of those are 0, so actually we want to put brackets there. And then the last interval would be from 2 to infinity. So this is the first one where we actually have 3 intervals in our solution set. How about that? Let me just fix this little box here. All right, there you go. So this is the solution for number 9. Number 10. Okay, so we got another one that we got to kind of rearrange and find common denominators and all that. So let's go ahead and get that started. So for here, we'll start, for this one, we are going to bring the 30 over 6x over to the left-hand side. The algebra here should be a little kinder to us than the last one because these denominators are monomials rather than binomials. So we've got 4 plus 1 over x minus 30 over 6x. The reason why that's relevant is because the denominator is going to be a little bit easier to find a common denominator. Like this one, I only have to multiply by 6 over 6 to get that common denominator. So like I can multiply this whole thing by 6x over 6x, right? So 6x over 6x like this. And then to get the common denominator over here, I'm going to multiply by, it would have to be, well, 6x times x is 6x squared, so we'll just go with that. All right, and that, you know what? I kind of don't like the way that formatted. This will be a little bit more consistent with the way I'm doing it. Okay, so this will get me the common denominator that I need. So I'm going to kind of clean all this up. I got 24x squared over 6x squared plus 6x over 6x squared. Oops. And then it looks like I forgot to multiply the last one, right? I need an extra x over here so that I have the common denominator. So this will be 30x over 6x squared. Okay, so now I got my common denominator, so I can combine them all, and I should be ready to start finding the numbers for my number line. So we've got 24x squared. No other square terms for the numerator, so that'll just stay the way it is. Then I've got plus 6x minus 30x, so that'll be minus 24x. Oh, look, this is going to work out real nicely. Over 6x squared. Okay, so now we can find our x-intercepts in the places that make it undefined. And I'm actually going to drag this work over a little bit to give me a little bit more room for this next part. Okay, so let me just move this up a little bit. So the numerator here is going to be 24x squared minus 24x. Well, that didn't really copy the way I wanted to. I don't know how that even happened. Okay, there we go. And so this is going to be one where we can factor out a GCF of 24x, leaving us with just x minus 1. And so we're going to get x equals 0 and x equals 1. For the places where it's undefined, we'll set the denominator equal to 0, and that'll give me 6x squared equals 0, so just x equals 0. This is the second time this has happened where we get the same number in both of these categories. But like we said before, if you get a number that makes both the numerator and the denominator equal 0, then it will be undefined. So this will kind of overrule the x-intercepts. So we actually do not have an x-intercept here. And like I said before, in the next unit, we'll go into more detail on what's actually going on there. So there's going to be two values I'm going to put on my number line here, just 0 and 1. So the representatives I'm going to pick are going to be, I'll go with -1, I guess 0.5, just 1/2, and then I'll go with 10. And so let's plug these in. So if I plug in -1, that's going to be, let's see, a negative times a negative will be positive over, so the denominator is always going to be positive here, because look, it's 6x squared, so I actually don't need to worry about that. And in fact, I neglected to show that this was actually going to have a multiplicity of 2. But yeah, so anyway, I do get a, so in other words, since it's always going to be positive, I don't really need to consider it. So I'm really just going to be looking at these two factors over here. And plugging in -1 gives me a negative times a negative, which is positive. This will be another opportunity to test out my theory about this even multiplicity. So I'm guessing that this is going to be positive as well. When I plug in 1/2, I do get a positive times a negative. Now hold on. Oh, you know what? I made a mistake here. Did I make a mistake? Negative times a negative is positive. Yeah, okay. And if I plug in 1/2, get a negative. So maybe my theory's wrong. Let's see, let me just double check real quick to make sure I did that right. Yeah, well, everything looks good here. And you know what? Now that I'm thinking about it a little bit more, we did have this exception for when the x-intercept was at the same place. On the last time that happened, let's see, which problem was that on? That was on number 6. We saw the same thing happen where the sign did change. So, but that was not one that had a multiplicity. I know we had one. Maybe we didn't. Maybe this is the first time where that multiplicity Okay, so it looks like there's a little exception from my theory, and that's when we have a hole in the graph, which we haven't really talked about yet. But basically, if you have, one of these x's kind of canceling out. So yeah, you just want to. I don't want. I think I'm going to stop talking about it just because I don't want to confuse you about like when it's going to alternate and when it's not going to alternate. If the multiplicity is 2 and you do not have a sort of like a conflicting x-intercept, I think it's still going to hold, but in this case it does not. It will alternate here. So if I plug in 10, I do get a positive. So I'm looking for where it's negative, and here it doesn't really matter where it's 0 and where it's undefined, just for the sake of staying consistent with my labeling. I'll go ahead and label this as 0, this is undefined. But my solution set is going to be everywhere where it's negative. It looks like that's just one set, and that's going to be in between 0 and 1. All right, we got 2 more problems, looks like. So number 11, let's get that started. Okay, so for number 11, we do need to find a common denominator. We need to move everything to the left side. So we got to do a little upfront work here, like in the last few problems. So we got 3x. One little piece of good news here is that it appears that we already have a common denominator. So that's pretty sweet. We don't need to worry about that. That'll save us a step. And so here we've got 3x minus 2x, which is 1x. So we've got x minus 1 over x plus 1. So this one's simplified real quick, real nicely compared to some of the other ones that are a little bit more complicated. So yeah, so that worked out pretty good. And actually, wait a minute, this should actually be plus 1. Check that out. So we got, this is going to be greater than 0. I think it's going to pretty much be greater than 0 for every number, because whenever you divide something by itself, you get 1. There's one little catch here, and if x is negative 1, this will be undefined. So it should be all real numbers except for negative 1. But let's see how this is going to actually play out if we just follow the strategy without taking these shortcuts. So if we know that x plus 1 is going to be 0, it tells us that we might have an x-intercept as negative 1, but as you already know, we're going to get that exact same value for this other column. It's going to actually make the function undefined. And just like what we talked about with the last problem, when that happens, the undefined sort of wins out. And so we're actually going to have no x-intercepts on this one. We're only going to have one place where it's undefined. And we should not expect the sign to change here. Again, this will make more sense in the next unit why that happens. For now, you can just kind of still use your representatives to test. But should be on the lookout for, be thinking about why that's happening. So my representatives here, I'm going to go with, I guess I'll just go with, well, negative 10 and 0 will do me just well. So let's see, if I plug in negative 10, I should get, I'm going to get 1. I'm going to get 1 either way, no matter what I plug in here, except for negative 1, right? So it's going to be positive across the board, except at negative 1, where the function is undefined. Make a little note there. So I'm not tempted to say negative infinity to infinity. I do need to break it up because I do not want to include negative 1 in my solution set. So I'm going to say negative infinity. Let's see here. I thought I had that in my... All right, there we go. So negative infinity to negative 1, and then also 1 to infinity. All right, and so that leaves us with one last problem here. This is the first and the only one that has a not equal to symbol. So we want to know when are these not equal. Okay, so when we bring this over, we're going to include both the positive and the negative sets here. So we don't need to worry about, doing the tests to see if it's positive or negative because we want both. So we don't need to distinguish between those. So really, we just want to know where is this thing 0, where is it undefined, and just exclude those from our solution set from the, just saying all real numbers. So let's first try to get this thing to have a 0 isolated on the right-hand side. So we go 1 over x plus 5 minus 2x minus 3 over 9 minus x. We are going to need a common denominator here. Let's see, do I have a not equal to? Yeah, there we go. So my common denominator, I'm going to have to multiply this one by 9 minus x over 9 minus x. And I'll multiply the second fraction by x plus 5 over x plus 5. Okay, I do need to do a little multiplication here. I'm going to leave the denominator factored because it'll just be more useful to me that way. But the numerator, before I can actually subtract them, I need to multiply these together so that I can get a common denominator and kind of go from there. So yeah, let's go ahead and do that. So this is going to be, well, 1 times anything is just going to be the anything, so that's not very interesting. And then over here, we're going to have 2x squared plus 10x minus 3x minus 15. And we can combine the 10x minus 3x to 7x. So now we're going to combine our like terms here. And this is getting a little cramped, so I'm going to make my font a little smaller here. So we'll start with my x squareds because that's the highest degree of any of those terms. So I've got negative 2x squared. So here, negative 2x squared. Let me just get rid of all this. We don't need this whole thing. Okay, so negative 2x squared, and then so for my x's, I've got negative x minus 7x, so that's going to be a minus 8x. And then I've got 9 minus negative 15, so that's going to be plus, well, let me think about that. It would be plus, why am I struggling with this one? Plus 6. No. Oh, gosh. It'd be 24. All right, so there we go. There's going to be, so we're basically looking to see, okay, where is this undefined? Where is equal 0? And we're just going to exclude all those values from our solution set. So we are not going to have to pick any representatives. We don't have to do all that. In fact, we don't even really need the number line here. I'm going to leave the number line, but I'm going to clear this out just because it's not going to be necessary. So we're going to see when is negative 2x squared minus 8x plus 24 equal to 0. And just to simplify that a little bit, I'm going to divide both sides by negative 2, just to kind of clean this up. So this divided by negative 2 would be 1. This divided by negative 2 would be plus 4. And this divided by negative 2 would be minus 12. 0 divided by negative 2 is just 0. And that'll just be a little bit easier to factor here. So two numbers that multiply to give me negative 12, but add up to 4 would be, what would that be, like 6 and negative 2. So x plus 6, x minus 2 equals 0. And so I'm going to get x equals negative 6 and x equals 2. So these are going to be where the function's equal to 0. We want to know where is it not equal to 0. So actually, now I'm thinking about it, well, it's definitely not equal. Yeah, I mean, over here, it's going to be undefined here, but it's not going to be equal to 0. So I think that's going to be a true statement. So I don't think we even need these values. I mean, just for the sake of doing it, I suppose. You can say that x could be negative 5, or x is going to be 9. But I don't, we're just wondering, hey, where is this not 0? And it's definitely not 0 here, so we don't really care about those. We're going to say it's not 0 everywhere except where it's 0. So we're going to say x can be anything except for negative 6 or 2. So those are really the only two numbers that matter here. We don't even need these. So this is kind of an interesting problem. I don't know that there's going to be one like this on the quiz or anything, but I think it's worth talking about just to really hammer home, what these inequalities mean and how do we interpret our findings here. So I'm not even going to go through and say what's positive, what's negative here. The only thing that really matters, again, is we care about when is this not 0. And so it's not going to be 0 everywhere except here and here. Okay? So we don't even care where it's undefined. It's going to be negative infinity. Oh, whoa, whoa. Negative infinity to negative 6. And then, let's see, then from negative 6 to 2. And then from 2 to infinity. And that'll be our solution set for number 12. That's it for today, y'all. What's going on with my parentheses there? There we go, kind of clean that up. As always, let me know if you guys have any questions. But other than that, y'all have a great day, and I'll see you next time.